form of another form of regression, which we call the non-linear regression. Of course, I'm going to tell you what makes it to be non-linear and not linear regression. Now, in the outline, oh, I remember this. I think I got some questions. Some students asked me questions about the idea behind it, using the stepwise regression and the variable selection in a situation where the predators are categorical. I think somebody asked me that question. That is actually beyond this class, but I'm going to give you the response to that, which I wanted to take notes. When you are working with the variable selection, okay, the backward elimination is still going to work great when you are dealing with categorical predators. But the forward selection will not work great. The forward selection, if you have a predator whose level is more than 2, the forward selection will always, it's not going to select, it's going to make them insignificant. It's going to take a wrong conclusion, making a predator whose level is more than 2 insignificant, even if it's going to be significant. Okay? So, but we have actually have advanced way, we have some packages have been modified, in a way to actually use variable selection when the predator variables are categorical. Like I said, the theory around that is beyond this class. So I'm just going to give you as information. Now, if you look at the ridge regression, or you look at the shrinkage, when you're working with continuous predators, of course, they actually work so great. But working with categorical predator, if you use a lasso and ridge, then you're actually going to take a wrong decision. So there's something that we call group lasso. Okay, group lasso that can be used in that situation. Okay, so which is also beyond this class. Okay, just for information, we call it group lasso. Okay, we use this group lasso when you're working with the categorical predators. But let me tell you this: when the both of them, when the predator variable and the response are all categorical, then we use a chi-square test of association. So this is just for information. Okay, so coming back to the nonlinear regression, the outline, I'm going to walk you through introduction to nonlinear, the different types of nonlinear regression, the intrinsically and intrinsically nonlinear, then logistic growth model, the Macaulay-Menten model, and Van Bantalaffi growth model. But you know what? There's a lot of story on Van Bantalaffi growth models. In fact, this model is very, very important for a state of Minnesota, and not only state of Minnesota when it comes to predicting the length or the weight of fish. We are a state that has to, or country that has to do with that into production of fish. Okay, so this is going to be reserved for Wednesday. But let's start with the introduction. Nonlinear regression. You remember the other time when we were trying to characterize everything that we have done up till last week. They are all linear regression, okay? But some of you may want, why are they linear regression? They are linear regression in parameters, okay? Before you can talk about linear, they have to be linear in parameters. It can also be linear in variables. But some of you may want to say, what about polynomial regression? Polynomial regression is also linear in parameters, only that it is not linear in variables. Not linear in variable, that's why you see S squared. Anything that is other than X. If you see any other transformation like log S, square root of X, X raised to power, that's a nonlinear. Okay, but the fact that the regression coefficients are linear, even though the variables are nonlinear, it is still called linear. Does that make sense? But in a situation where you have non-linear in parameters, when you talk about non-linear in parameters, you are no longer talking about linear. It doesn't matter if the variables are linear, but the fact that it is non-linear in parameters, of course, it is no longer a linear function. Okay, and that is why we emphasize on non-linearity of parameter. Okay, that's why I say if you take a look at that, I said the mean of the response variable is not a linear function of the parameters. Now we got two types of non-linear models. Let's say now you now know what we mean by non-linear models. By non-linear regression models, we're trying to say, okay, it is non-linear in parameters. That's what we mean. And non-linear in parameter, maybe you're basically going to have a parameter divided by another parameter, because what we have been having is we're adding, right? We've been adding or subtracting. That is still linear. But situation where the parameters are now being multiplied, or something is raised to power the parameter, or other algebraic transformation is on that parameter, that it is non-linear. Now we have some linear model. We have some non-linear models that can be linearized. I'm going to say that again. We got some non-linear models that can still be linearized. If we can linearize them, then they become intrinsically linear models. Intrinsically linear model means initially they were non-linear, but after transforming them, they become linear. An example is logistic regression model. Now, if you take a look at what I'm trying to show you now, this is looking like a linear now. Initially, it was not like this because, of course, that's what we're going to do next week. Chapter 12 is basically on logistic regression model where the response variable is no longer continuous. In linear regression, it is required that the response variable has to be continuous, right? But the moment the response variable is no longer continuous, if the response variable is categorical, you're basically going to go for logistic regression. But you know what? How do we go? How do we derive logistic regression? If I want to walk you through that in this class, if I want to go through theoretical derivation of that, we basically started from linear regression. So we generalize linear regression to arrive at this. This is an example. So here now, a linear approach can actually be used, except that the whole of this now is going to be the new variable for the response. And the parameter beta 1, beta 2, they are say in linear form. Therefore, the linear approach can actually be used in this situation. Now, I want to show you another non-linear, non-linear model now. This is another example of non-linear model. You can see the predators are even carrying the parameters. Okay, but when you take a look at this is looking like a Cobb-Douglas in economics, where we're actually looking at the output in relation to the input, capital input and labor input. When you take a look at this, oh my God, this is, if I take a log of this, I'm actually going to have this guy. It has been linearized already. Look at that. This is now linearized now. Okay? So these are examples of intrinsically linear models. Initially, they were not linear, but with a certain transformation, they become linear. And of course, if they are now linear, then the linear approach can actually be used to estimate the parameters. Okay? I wanted to take note of that. But let me tell you this. What if I have, when you take a look at this Cobb-Douglas now, the way error comes into the model here, okay, if this is what I have, if I have yi equal beta 1, okay, and x to beta 2 and x3 beta 3 plus ui, then this become intrinsically non-linear. because there's no transformation here that would make this to be linear, because look at the way the error is coming into the model. Do you see that? But here, of course, this can be linearized, okay? Because we have different versions of Cobb-Douglas. You know, the way error comes into a model. Error could come into a model in an additive way. Error could come into a model in a multiplicative way. Okay, so all what I'm just trying to tell you now is we got some models that are not linear, but they can actually be linearized, and there are some that cannot be linearized. Okay, so this one can be linearized. This is a Cobb-Douglas. Okay, but this one now cannot be linearized. Okay, there's no any transformation that will make it linear because of plus this. Okay, except we're going to go by a way of Taylor series, which is an approach, you know, an iterative procedure, because we have a situation where we got nonlinear, and of course we realize that they cannot be linearized, and we still want to estimate parameters. Then we're actually going to go by way of approximation, and that is where the Taylor series comes in. Okay, this is where you're going to talk about numerical approach like Newton-Raphson method of iterative way to arrive at the optimal values of the parameters. Okay, I just wanted to take note of that. Now, this is another model here, which is another version of Cobb-Douglas. Of course, we call that constant elasticity of substitution. We call this guy here constant elasticity of substitution. Okay, of course, there is no way this can be linearized. No way. A lot of parameters say they are multiplicative. The only thing we can do here is basically to use Taylor series of approximation. Okay, so take a look at it. I'm just trying to show you now different kinds of nonlinear models that we have. Those ones that can be linearized and those ones that cannot be linearized. Okay, go ahead.
Like the differentiating, like are we categorizing like GLMs with this, or are we saying like non-parametric regression?
Oh, that's another. You get to another realm, because we're talking about non-parametric regression. That is where you don't put into consideration the assumptions of normality and the like. Where you are talking about quantile, that's a different stuff. You know, that comes in when you no longer, maybe the assumptions of parametric is not met and you want to go into. But here we're talking about, we're not talking about assumption now. We're focusing on the mathematical architecture of the model. You know, the one we were working on before, we've been using linear, you know, assumptions of normality, constant variance and the like. That's actually based on the fact that we already have a linear relationship. You get what I mean? So, but now we get a different kinds of, form. So, which means a mean function can be in different forms, except that we just need to recognize that. Okay, now I want to take you, now when you take a look at this is an exponential model. Of course, when you take a look at this, that's a linear regression, right? But when you take a look at this is not linear. Okay, when you take a look at this guy now, it's a non-linear. And this is an intrinsically non-linear. Why? Look at the way error comes in. This is an exponential model. We use this in GDP, money supply, and so on like that. You understand what I mean? So this is an exponential model. Okay? So take a look at that. Now, I'm going to show you another form of nonlinear regression model, logistic growth model. Okay? Of course, this can actually be used to project population of a particular country. Okay? And when you take a look at what I have here, this is looking like an intrinsically nonlinear model. Okay? You know, the theta one here may be talking about the maximum capacity of that particular population. You can see here you are dividing the other parameter. Look at that, theta 1 divided. That is a way to tell you that you are working with a nonlinear regression model. And when you take a look at this, okay, you may not be able to linearize it. But let me tell you something. If you linearize, at times we can try and linearize it, but when we linearize this, maybe we basically want to, whatever we get in terms of theta 1, theta 2, theta 3, will be used as initial values. Because if you want to do iteration, right, you need a very good initial values, right? You know what I mean by initial value, the starting point, right? And you have to because we want a situation whereby we're looking for the values of parameters, theta 1, theta 2, theta 3, that will minimize the unexplained. Even in non-linear regression, we also want to minimize the unexplained variation. Only that we are seeking to get the optimal values of theta 1, theta of the parameter that will do that will minimize that. But we actually need a good start. Okay, what is going to be the initial value of each of that? And what we normally do is we don't just guess initial value. It may not converge on time, and what we do, we can try to see whether we can linearize it in a way, okay, to be able to estimate the initial values then that will now be used in the iterative process. Okay, so let me just tell you generally, we have a model which is ms of theta plus the error, which we call the nonlinear. That ms of theta is nonlinear. And what we basically want to do is to minimize the residual sum of square, but at times we could assume that the weight, we may not have a constant variance, and we can have a constant variance. Situation where we may not have a constant variance, we're actually going to introduce weight. Look at that. We're going to introduce weight. Okay, so in that situation, we're trying to say it is no longer sigma squared, but sigma squared divided by W. You remember what we did under the weighted least square. Now, you know what I want to do now? I want us to look at that logistic regression model. We want to go into population projection using logistic regression model. Okay, we have different kinds of models we use in statistics to make a population projection. Not only population projection. I could remember, when you want to predict the number of cases of a particular disease, like number of cases of COVID. Of course, we have different kinds of nonlinear models that can be used in that regard. You could talk about exponential model, but the exponential model, the disadvantage of that is just like it's going to go out of bounds. Okay, but we have a logistic regression model. This is different from logistic regression. Sorry, let me say logistic growth model. Because we're going to do the logistic regression model next week. This is logistic growth model is different from logistic regression model. Does that make sense now? The logistic regression model we're going to do next week is when the response variable is categorical. But here, this is for growth model, where the response variable is not categorical. Does that make sense, right? Okay, so now we have this models. This logistic regression model. These are examples of a non-linear regression model, and we basically want to estimate parameters. And let me tell you this, to estimate parameters here, because this is an intrinsically non-linear model, okay, because when we linearize that, okay, we may not be able to linearize that. I'll be able to use method of least squared, and the result, so because of that, we're basically going to use a Taylor series expansion. Okay, the idea behind the Taylor series is more or less like, okay, how can I actually have an approximation, okay, by non-linear in a linear way? Okay, even though I know there's going to be loss of some information, that's no problem at all. Okay, so that's exactly what we're going to do, and we have different ways to do that. Okay, we can actually use what I call Gauss-Newton, Newton-Raphson, and so on like that. So I'm going to take you there now. Okay, this is I'm coding that in R. Look at that. I'm trying to code that in R now. You know what I want to do? Okay, I basically want to predict population given year. Look at that. That's why it's a growth model. I'm going to go back to the model so that you'll be able to see. You see? Okay, you see that, right? This is a model, right? This is the theta 1, the theta 2, the theta 3, right? My x is going to be year. My y is going to be the population, right? Okay, I want to try that now. Okay, now I write the coding out. See the coding out, right? Okay, now because this cannot be linearized, because this is an intrinsically nonlinear model, and what we're basically going to do is to probably seek redress in, optimization using the iterative means. Okay, then I need a good starting point to do that. That's what I'm trying to do here. Look at that. Most nonlinear least square algorithms require specification of starting values for the parameters. Okay, the theta 1, the theta 2, the theta 3. You can't just guess them. And what we're basically going to do is we can look at the model and try to see if we can linearize it in a way, right? The linearization we want to do here is just to get the starting values. The values we're going to have here, they are not the optimal values we are looking for. Okay? Now, you're going to see what I'm going to do now. We're going to use the knowledge of mathematics. That's why mathematics is very, very important. Now, I'm going to divide the population by the carrying capacity. Okay? See? Divided by theta 1. Now, take a look at what we have now. Then, I'm actually going to solve this mathematically. Of course, you can see an exponential, right? At the end of the day, you're going to have log of that equal to that. Oh, my God. Looking like something like a linear, right? Look at that. The whole of this now is more or less like a new variable. But don't forget, a new variable that depends on theta 1. And that is the reason, the one the one I showed you in the logistic regression the other time, the new variable does not depend on any parameter. But the one that depends on a parameter, of course, the only good thing we want to get out here is basically the starting values. Okay, now when we have this guy now, then we have a code. Now, you need to load a package called car. I basically want to focus on United States population. Okay, take a look at that. Okay, so in the data for United States population, of course, the data has year and the population at a given time. Okay. Oh, you want to ask a question? Okay. Now, the next thing I'm actually going to do here, okay, the coding, I'm going to do population divided by 400. Why 400? When I look at the data, I will look for a reasonable value that is bigger than some value. Of course, the United States population now is not up to 400 million. You know that, right? I can choose a number like that, like a 400, which is the maximum. I'm talking about the number, that will be greater than when you look at the data that we have. There's no 400. They are all less than 400. Don't forget here, when we're looking at the logic, we divided this by theta 1. That theta 1 is more or less like the maximum capacity. You get what I mean? Then you have to think of the reasonable values. That's why. So when you do that, we have these two. We have these values now. Don't forget. Theta 1. We think about this ourselves, looking at the data. Now we now have some values now. Okay. The other ones. Don't forget. Let me show you the one. The theta 2 and the theta 3 is the one that you got out. The theta 1, you think about it, looking at your data. The value that is greater than the values in the population, you choose 400, right? Now, what we're trying to say now, we are now set. We are now set. We got 3 values now that will serve as a starting point. For theta 1, 400. This guy and this guy. No, those 3 values now will be used as a starting values. Does that make sense now? Okay. Now I'm going to go into the code now. Oh my God, I'm actually stating them. Okay, now this is it. NLS means non-linear least square. We use non-linear least squared when you are trying to figure how you want to estimate the parameters in a non-linear regression model. Now you write the function again, right? And you have to start equal to least. Oh, theta 1, 400, theta 2, this, theta 3, that. Of course, you know how I estimated that, right? Now, all this is going to come out because it's going to be going, and it's going to get to a point that it's going to converge, right? So take a look at that, okay? And you're going to see when you get to around here, it start bringing the same, right? Take a look at that, okay? So in the end, we have a result, okay? In the end, we basically have a result. By the time you do this pop.mode, you can do the summary of that. Then you're basically going to have, look at that. You do the summary of that. Then you are back at, oh, sorry, this doesn't line up. Okay, these are the estimates, the standard error. These are the p-values. Okay, so take a look at that. Now, the estimate of the parameters now, theta 1 is now this, theta 2 is that, theta 3 is that. Any question? Look at that. That is how we estimate that. They were using the idea of, nonlinear least square, where this is an intrinsically nonlinear regression model. It is called an intrinsically nonlinear regression model because it cannot be linearized. Since it cannot be linearized, you cannot use a linear, the least square approach. And what you're going to do is to use a non-linear least square. The non-linear least square, basically, we're using the idea of, iterative procedure. Okay, so take a look at what we have. Okay, so now look at my interpretation now. Said the column mark estimate display the least square estimate of the parameter. The estimated upper bound for the U.S. population is thus 440.8. Okay, which is about 441 million. Okay, that is judging from the theta 1. Okay, that's judging from the theta 1. Okay, so 441. Okay, so take a look at that. Okay, so and I said the column mark standard error display the standard error of the estimate. Of course, now we are back at what we normally do in linear regression, where you have the estimate, then you have the standard error associated with that, and all these are only okay if we're talking about last sample theory, asymptotic, right? Okay, these are okay. So you can do confidence interval. You can do a test on the parameters. That's why you got a p-value, right? So take a look at that. Now, any question on that before I go to the next module of the day? Any question on that? Okay, so now the next one is a Michaelis-Menten model. Okay, when you take a look at in this model, the parameters is V and K. Okay, VM and K, those are the parameters. And the way it appears here, this divided by that, that's a nonlinear. Okay, so I wanted to take note of that. But do you know we can actually try and see how we can make this in a linear way? Let's take a look at that. The way we can arrange this in a linear way. Okay, now if this is Y and I want to make it the reciprocal, then I'm actually going to switch, right? That's why I'm switching this, right? Get a 1 over Y. Now, K plus S divided by this, I can do K divided by that plus that that's what I have here. Okay. Now, and you take a look at what I have now. You have this, you have that, 1 over Y. Okay. And of course, the S cancel X. Then this is more or less, 1 over Vm, where Vm is a parameter. 1 over that's another parameter. That's a constant, right? And this is more or less looking like, K divided by that S, like a reciprocal of X. So this is looking in a way, maybe in a linear form, right? Take a look at that. Okay, so that you can actually say that, okay, this can be beta naught, okay, and this guy here can be beta 1, okay, so that you can actually say that, okay, your VM equal to that and your K equal to that. Okay, don't forget, what we're looking for initially, what we're looking for is VM and K, but believing that when we go by way of linear regression, if I get your beta naught and beta 1, then we'll be able to get this guy and this guy. So take a look at that. So we're going mathematical now. Now we actually want to apply this because market lists are maintained and has actually been used to capture relationship between rate and concentration. For those of you who is there anybody from chemistry? Okay, good job. Or from biology, like something biological related. I know you're familiar with stuff like this. Okay, so now we may want to look at the relationship between the rate and concentration. Okay, and by the time we plot them, okay, you know, when you generate the scatter plot, you can actually see this is not a straight line at all, right? Take a look at that. It's not a straight line at all. Okay, so how do we model this? Of course, this particular model has actually been used, okay, to capture that. Okay, is working for something like that. Okay, so and that is the reason why we want to try using that now. But let me tell you, if you want to start using that, the idea here is basically, you know, what we're trying to do here, okay, don't forget, okay, we believe that this is a way to get our VM and K after trying to linearize. Now, let us now use that here now, okay. Now, what is our X? X, the new variable, is 1 all over concentration, okay, and Y equal to that. Okay, look at how do I get that? I want it to go back to here. Look at that. Can you see that now? Okay. You see all these guys, right? You see them? Okay. So now when I'm trying to, trying to model that, your X new is 1 over cons and Y new. Okay. The Y new is minus 1 divided by rate model less than lm y new on x new. Okay, it's like you have a y new, you have x new, and of course, how do I know that my k equal to module coefficient 2 divided by that? I'm going to go back. You're going to see k is actually beta 1 divided by beta naught. You see that, right? Okay, so I just wanted to take note of that. And the v is 1 over beta naught. So look at that. If you don't get your mathematics right, you may not be able to do the coding well. Okay, so now that is what I have. And here, the idea here is just for me to get the values that I'm actually going to get. They are not the optimal value. Maybe the starting point. Does that make sense? We need a starting point. These are intrinsically non-linear model. Okay, so starting point. Now take a look at this now. Okay, and now I want to do the model now. Okay, we rate on here. I'm actually going to write the whole function. Don't forget the function, the way the function actually look. Rate on that. Don't forget, rate is like y equal. Let me take you back so that you'll be able to see what I'm talking about. Okay, so this is look at that. This is your y rate equal to that. By the time you want to run that in out, you need to be able to code it the way it is. That's exactly what you are seeing here now. You see that? You see that? VM, this is like X, okay, divided by that. And your start list is what you got. Okay, that was the essence of the transformation in the first place. Okay, what you got. Okay, and the idea behind is this, and the idea behind this code is the mathematical operation that you perform the other time. Like I told you, these are intrinsically non-linear models. All what you just need to do is for you, we are linearizing this The linearization here is not it's not a complete one, but it's the one that will enable us to figure out the starting values. Like I said, now the starting values that we got is what we plug in, and at the end of the day, I'm going to show you a result. Here we have used Gauss Newton iteration method. There are different kind of iteration method you can use. It to Raffington, first position. There are Jordan, and there are a lot of them. But of course, the Gauss Newton actually has a reputation. Now, take a look at that. This is a way you're going to have before the something actually converge. Okay, so that's exactly what you actually going to have. And in the end, these are the parameters, the 17.07906 and 126 points. So take a look at that here. You can see the last value there. Okay, this is the last value there, right? Okay, but let me tell you this. You'll be able to get to your results on time if you start with a very good, initial value. But if you start with initial value that is not reasonable, you're just going to be walking around. It could take forever. You get what I mean? So, and we believe that when you linearize in a way, you'll be able to get the starting point, the starting initial values. A very good one. Okay, so that is that. Oh no, this one is not for today. I still have like 10 more minutes. Okay, I'm gonna